Hello, as a junior at Dongguk University, we will present two types of DRAMs designed by ourselves using the Cadence tool this time. As you can see, the basic structure of DRAM, if you look at the left side of the screen, the most basic DRAM is a 1T1C structure with one transistor and one capacitor. Here, the transistor acts as a switch controlled by the word line signal, and the capacitor stores the data coming through the transistor in the form of an electric charge. However, to increase the stability and accuracy of the data, we adopted the 2T2C structure on the right in this design. The 2T2C structure uses a pair of complementary bit lines with opposite signals along with the bit line. It stores data in two capacitors with opposite values and uses a differential method that takes advantage of the voltage difference between the two signals to read. This method can maximize the reliability of the data by minimizing external noise and reducing data distortion. Therefore, our design also consists of two transistors and two capacitors to ensure this stability. Next, we will talk about write operation. Write behavior is divided into two processes, write high, which writes data 1, and write low, which writes data 0. First, it is the write high processes on the left. Write stores data 1. A forcing is performed to apply a voltage of 1.5 volt to the bit line. In this state, when the transistor is turned on by activating the word line, the current flows from the bit line to the capacitor. As a result, the high data is stored as a capacitor's node voltage. Vx is charged from 0 voltage to 1.5 voltage. Conversely, write low processes on the right when storing data 0. 0 voltage is applied to the bit line. When the transistor is turned on by activating the word line, the charges stored in the capacitor are discharged toward the bit line. This causes the node voltage Vx to drop from 1.5 voltage to 0 voltage, completing the low data writing. In conclusion, charging and discharging the capacitor according to the bit line voltage while the word line is active is the core principle of the write operation. Read operation. The read operation basically uses the principle of a CCL between bit line and cell capacitors. Between sharing the operation, the bit line voltage is first precharged at the level of VDD over 2, which is half the power supply voltage. First, it is a read operation of a typical GND forcing structure shown on the left. The lower part of the capacitor inside the cell and the parasitic capacitor on the bit line are both tied to ground. When the word line is activated in this state, charge sharing occurs. If the stored data is 1, the voltage will rise slightly above the bit line precharge level, and if the data is 0, the voltage will fall slightly below the precharge level. As a result, only a very minute voltage changing occurs in the bit line depending on the data, and this minute signal difference is transmitted to the sense amplifier at a later stage to be reliability amplified and discriminated with high and low data. Next is the half VDD forcing structure that we applied, shown on the right. This structure also applies the charge sharing mechanism with the bit line precharge to VDD over 2. Mathematically, the final voltage change detected by the sense amplifier in the event of charge sharing is exactly the same as the GND method on the left. Since the reference voltage of both the bit line and the lower capacitor are VDD over 2. In other words, the accuracy and reliability of the output data are the same. However, there is a critical difference in precharge power consumption immediately after the read operation. The GND method of the left requires the charge to be consumed when the bit line is precharged again for the next operation after the read operation. but the VDD/2 method on the right allows the bit line charge to be recycled without the charge being discarded during the pre-charge stage, because the lower plate itself holds the VDD/2 reference point. As a result, the read operation principle of the two structures and the signal magnitude determines are the same. But the right structure can drastically reduce the charge-discharge dynamic power consumption of the bit line, which is much more advantageous for low-power DRAM design. I will start with the smallest unit for hierarchy of DRAM. Our design of DRAM has also gone from the bottom of this hierarchy to the top. First, at the bottom layer, there is an array structure of cells, the basic unit that stores data. As you can see, it is the smallest unit that makes up 60-bit with a 4-4 structure. And you can see it as an example that is not related to our design. These arrays come together to form a bank that can handle commands independently. And when these banks are grouped together again, it becomes one complete independent semiconductor part, the DRAM chip. In the figure, 8 banks come together to form one chip, a unit that arranges multiple DRAM chips on a printed circuit board. For simultaneous access is called a rank. Finally, the rank structure combines the front and back to form the final memory module, DIMM, which is mounted directly on the motherboard. This DIMM module will then send and receive data to and from the processor through channel, which is an independent data channel that connected to the system bus. In conclusion, we have completed this DRAM design in a hierarchical way, starting with the design of the smallest cell and array and considering the final chip and module type. Next, we will discuss the peri circuit, a peripheral circuit that supports the core operations of DRAM. The first peripheral circuit is the pre-charge circuit. As previously discussed in read operation, the voltages on both bit line must be equally matched to the VDD/2 level before data is read. When the pre-charge enable signal is applied, the VDD/2 voltage is supplied through the upper two transistors. At the same time, the equalizer MOS marked in the middle red box is turned on to balance the voltage on the bit line and the complementary bit line at the same level. The second peripheral circuit is a bootstrap circuit that raises the voltage of the word line to a higher level than the supply voltage VDD. The NMOS transistor inside the DRAM cell loses voltage by the threshold voltage of the transistor itself when delivering high data. To write or read complete high data into the cell without such voltage loss, a higher voltage than VDD must be applied to the word line. To implement this, we analyzed and applied two types of bootstrap circuits to the design. First, the first design circuit shown on the left. The structure operates on the basis of clock inputs and pre-charges the nodes through the internal inverter chain and pass transistor structure before performing capacitor pumping by controlling the output according to the timing of the clock signal. The clock synchronization system has the characteristic of forming a stable pumping voltage. Next is the second type of circuit shown on the right. The circuit artificially pumps the output voltage using internal independent delay elements and capacitor parts CBS when the word line input signal comes in. By precisely adjusting the delay time of the input signal itself through the control block, It is a structure that accurately raises the word line output above the VDD at the desired time. As a result, both circuits have the same purpose of pumping voltage to prevent threshold voltage loss, but they differ in the timing control method and device configuration to raise voltage. Based on these characteristics, we designed the optimal bootstrap circuit to meet each specification requires of the variable DRAM architecture. Finally, the sense amplifier circuit is responsible for the most important role in the Paris circuit. As you have already seen, the difference in bit line voltage immediately after going through charge sharing is very small, with only 0.07 voltage. This microscopic signal is very vulnerable to noise and this state cannot tell the data. Therefore, we designed a sense amplifier with a cross-coupled inverter structure. When SAP and SAN signals are activated with a slight voltage difference, the upper PMOS pairs M1 and M2 and the lower NMOS pairs M3 and M4 operate with positive feedback. This process amplifies the bit line, which has a relatively slightly higher voltage, to a full supply voltage level of 1.5 voltage, and the complementary bit line, which has a low voltage, drops completely to 0 voltage. As a result, the sense amplifier is the most important circuit in determining the reliability of our DRAM design, restoring and amplifying microscopic analog signals to perfect digital high and low data.
Next, we will discuss the DDR or dual data rate method for determining data transfer rates. This slide shows a comparison of the timing diagram of the DDR method applied to our design with the traditional SDR method. First of all, if you look at the SDR method at the top, only the rising edge where the clock goes from low to high will send data. You can see that the data output only occurs at the timing of the red arrow in the figure. That is, it's only processed one data per one clock time. On the other hand, the DDR method at the bottom sends data not only from the rising edge, where the clock goes up, but also from falling edge, which goes down from high to low. As you can see in the figure, the data output occurs in both the red and blue arrow timings. As a result, comparing to data output waveforms below shows that within the same clock frequency, the DDR method transfers twice as much data as the SDR. In this DRAM design, we adopted this DDR method to double the bandwidth and maximize the data transmission speed even in the same clock frequency environment. Now I'm going to talk about the final full chip structure, which is based on the hierarchy that I mentioned before. And this slide shows the architecture of the entire chip that was actually completed. If you look at the red box at the bottom right, you can see the 4x4 array structure, which is the basic building block. The 4x4 array currently displayed on the screen, or the layout of the entire chip, is just one example for better understanding. The final design we designed is not fixed in this chip. The key to our design is flexible scalability based on application specification. We designed the number of arrays and bank deployments to be completely different depending on whether the final target is a low power or higher bandwidth oriented GDDR. The comparative analysis of the number of arrays and bank deployments for each will be explained in more detail later. Based on this scalable architecture, the MUX structure on the right efficiently controls the data signals of each layer sent by specification and finally transmits 4-bit data. In conclusion, we implemented the array as a building block starting with the unit 2T2C cell and completed the full chip design that can flexibly respond to the market's requirements such as LPDDR and GDDR. Next is the results of the schematic and layout of Bootstrap that we designed ourselves. If you look at the schematic at the top of the screen, the inverter chain structure, the delay element, and the capacitor component are designed to be heterogeneously connected on the cadence tool, as explained in the previous principle. In particular, we focused on optimizing the size and delay time to the inverter to ensure a stable pumping voltage. Based on this schematic, the layout results at the bottom are physically drawings placed on the actual semiconductor chip. As you can see, many inverter elements are regularly arranged horizontally and regularly, and metal lines have been routed tightly to minimize voltage loss or signal delay due to parasitic components. The brown area on the right is the bootstrap capacitor area. Due to the limitations of the process technology currently available in our undergraduate research environment, the capacitance value per unit area was low, so we had to use a capacitor of this large physical size to meet the target capacity. Although the area was increased due to the process limitations, we succeeded in stably securing the desired bootstrap voltage level in this simulation. This is the circuit and layout design result of sense amplifier, which is the most important part of DRAM design. The schematic on the left shows a cross-coupled structure to amplify a minute differential signal. The PMOS and PM2 and PM3 are symmetrically arranged at the top, and NMOS and NM3 and NM4 at the bottom. In order to accurately and quickly amplify the minute voltage difference between the two bit lines, we focused on precisely matching the width and length sizes of the transistor on the left and right sides of the transistor to be exactly the same. If you look at the layout on the right, we tried to physically realize the perfect symmetry of the schematic. The PMOS area to which the SAP line is connected is laid out in the horizontal symmetry and vertical layout structure, and the NMOS area to which the SAN line is connected at the bottom. To prevent signal distortion, we finished routing by matching the pattern length and thickness of the bit line and the complementary bit line equally. Next, we are going to start with a detailed comparative analysis of the variable architecture that we've actually done with the layout. First, we are going to do a comparison in step 1 array. The LPDDR on the right and the 8 to 8 cell structure with 64 cells connected in one array. The unit array was enlarged to induce the sharing of peripheral control circuits such as sense amplifiers and decoders. This method drastically reduces the area overhead of the entire chip. GDDR on the left, on the other hand, adopted a 4 to 4 cell structure that splits the area size into 16 cells. Reducing the array size dramatically shortens the physical length of word lines and bit lines and minimizes the parasitic capacitance and resistance components to maximize signal speed. The following is a layout comparison in the one bank phase formed by these arrays. The LPDDR on the right is a structure that simplifies the entire chip to a total of 4 banks by placing 4 large 8 to 8 arrays you saw earlier. In contrast, GDDR on the left has 8 bank split structure that places 8 small arrays of 4 to 4 and doubles the number of independent banks compared to LPDDR. This enables high bandwidth data processing by securing bank level parallelism or bank level parallelism. Finally, we compare the overall shape of the final full chip layout of the two architectures. The LPDDR full chip on the right has completed a mobile, low power intensive orientation layout that shares the surrounding control circuitry as much as possible and increases the array density. The cell array accounts for a very large percentage of the total chip, making it the best layout for extreme savings in area and power. The GDDR full chip on the left, on the other hand, is a graphically oriented layout for ultra-fast bandwidth, and the array is divided into small pieces and independent banks or increased sense amplifiers and decoder routing circuits are densely distributed throughout the chip to create a complex and colorful symmetrical structure. As such, we have successfully implemented a variable full chip design that takes completely different internal layers architecture to target specifications. From now on, we will compare and analyze the quantitative design result data of the two architectures described earlier through the table. The first is the power attribute. LPDDR with A structure shows 381.15 microwatt of power consumption, and GDDR with B structure shows 414 microwatt of power consumption. By minimizing array division, we can see that LPDDR with shared peripheral control circuit has a definite advantage in terms of power consumption. Secondly, delay, or the operating speed characteristic. LPDDR shows a speed of 55.4 nanoseconds due to line delay, while GDDR dramatically reduced the line length, achieving an overwhelming ultra-fast response speed of 0.138 nanoseconds. In terms of speed, GDDR has a very strong advantage. Third, the area. Area characteristic. LPDDR is about 584,333 micro square meters, while GDDR with redundant peripheral circuits expands to about 728,121 micro square meters, showing that LPDDR is superior in terms of integration. Finally, the PDA results, a comprehensive performance indicator, shows a much lower PDA indicator of GDDR, a B structure whose speed performance was overwhelming numerically, showing a good comprehensive balance. In conclusion, we completely validate two different DRAM design results: graphic-centric GDDR, which traded off area and power to maximize performance, and mobile-centric LPDDR, which sacrificed speed penalties instead of saving area and power. That's all for our presentation, and thank you for listening.